Hello everyone, this is John Hashmat and welcome to Physics Simply. In this video I will be solving the paper for exam for October-November 2018 variant 1. So let's get started. Question 1 says a train of mass 5.6 times 10 to the power of 5 kilograms is at rest in a station. At time t equals 0 seconds, a resultant force acts on the train and it starts to accelerate forwards. Figure 1.1 is the distance time graph for the train for the first 120 seconds. Part AI says use figure 1.1 to determine first the average speed of the train during the 120 seconds. So this is total distance divided by total time, and we have the total distance at the top of the line here. This is at 4,800 meters. So the distance 4,800 and the time is 120. That gives an answer of 40 meters per second. And part 2 requires the speed of the train at time 100 seconds. And at 100 seconds, the graph is a straight line. So we use the gradient of the line to get the speed. For example, we can use this point and the point at the end. So we have coordinates 4,800, that's point 2, and 3,600.1. And for point 2, the x coordinate is 120 and x1 is 100. First, we write that the speed is equal to the gradient, and then we substitute y2 minus y1, 4,800 minus 3,600, over x2 minus x1, 120 minus 100. That gives an answer of 60 meters per second. Double I says describe how the acceleration of the train at time t equals 100 seconds differs from the acceleration at 20 seconds. At 20 seconds we still had acceleration because the graph was still a curve with increasing gradient, but at 100 seconds it was a straight line, which means this is a constant speed, so the acceleration is 0. We can write that the acceleration at t equals 20 seconds is greater than 0, and at t equals 100 seconds is 0. No acceleration. Part BI says the initial acceleration of the train is 0.75 meters per second squared. Calculate the resultant force that acts on the train. We can use F equals ma, and we have the mass at the start of the question, 5.6 times 10 to the power of 5, and the acceleration here is 0.75. This gives an answer of 4.2 times 10 to the power of 5 newtons. Double I says at time t equals 120 seconds, the train begins to decelerate. State what is meant by deceleration. It is the rate of decrease in velocity. Question 2 says figure 2.1 shows a uniform plank AB of length 2 meters suspended from two ropes X and Y. The weight W of the plank is 210 newtons. The force in rope X is P and the force in rope Y is Q. State in terms of P the moment of force P about point B. So we must say that the distance is from this force to the point B, which is 1.5 meters, and the magnitude of the force is P. So force times distance, or distance times force, that is 1.5 times P. Part B says calculate the moment of W about point B. We have the force, the magnitude of the force, and this was a uniform beam. The distance from B to the rope X is 1.5, and from X to A is 0.5, so the total distance is 2 meters, and this distance is half 2 meters, so this is 1 meter. So calculating force multiplied by perpendicular distance, we have 210 newtons multiplied by 1, so the answer is 210, but the unit is Newton meter. Double I requires the force P, and triple I requires force Q. Since we have two unknowns, and Q is acting at point B, we can take moments at B to cancel the effect of Q as a moment, because there is no perpendicular distance from rope Y to B. And then we can say that P creates a clockwise moment and the weight creates an anti-clockwise moment. And since this is in equilibrium or at rest, we can say that the clockwise moments are equal to the anti-clockwise moments about point B. And the clockwise moment is equal to 1.5 times P. The anti-clockwise moment was 210. We can divide by 1.5 on the right side to get the value of P. This gives an answer of 140 newtons. Now we can use the other condition for equilibrium, which is resultant force is equal to 0, or the upward forces are equal to the downward forces. We have two upward forces, P and Q, and we have one downward force, 210. So we say that P, which is 140, plus the unknown force Q, is equal to the downward force, 210. Then we subtract 210 minus 140. That gives an answer of 70 newtons. Question 3a says state what is meant by the principle of conservation of energy. It states that energy cannot be created nor destroyed. it can only change its form. Part B says figure 3.1 shows a girl throwing a heavy ball. State the energy changes that take place from when the girl begins to exert a force on the ball until the ball hits the ground and stops moving. First, the change was from chemical energy stored in her body to kinetic energy given to the ball, then to gravitational potential energy as the ball rises. Then gravitational potential energy is converted to kinetic energy as the ball falls, and then to sound and heat as the energy dissipates when the ball hits the ground. Double I says the mass of the ball is 4.0 kilograms. The girl exerts a force on the ball for 0.60 seconds. The speed of the ball increases from 0 to 12 meters per second before it leaves the girl's hand. First, calculate the momentum of the ball on leaving the girl's hand. Momentum is equal to mass times velocity. So we multiply 4 kilograms by 12 meters per second. That gives an answer of 48 kilograms meters per second or Newton second. Then we are required to calculate the average resultant force exerted on the ball. So the force is equal to the change in momentum over time. And the final momentum was 48. The initial momentum is 0. The time here is 0.60 seconds. This gives an answer of 80 newtons. Question 4a says figure 4.1 shows a liquid in a cylinder. The depth of the liquid is 10 centimeters and the radius of the cylinder is 3 centimeters. The weight of the liquid in the cylinder is 2.5 newtons. Calculate the density of the liquid. Density is equal to mass divided by the volume, but we do not have the mass or the volume. We can calculate the mass by dividing the weight by g, the gravity field strength, and then we can get the volume by multiplying the area by the height. So the weight is 2.5, g is 9.8, and we divide by, for a circular cross-section area, the area is pi r squared, and the radius here must be in meters, so it is not 3, it is 0.03 squared, and the height is also divided by 100 to convert from centimeters to meter, so it is 0.10, not 10. This gives an answer of 902.239. We can approximate that to 902 kilograms per meter cubed. Now the rest of the question includes manometers which were removed from the syllabus, so you can skip this part. It says figure 4.2 shows a device that measures the pressure of a gas supply. State the name of the device. This is a manometer. It compares the gas pressures on both sides of the tube. Double I says the difference H between the two liquid levels is 2 centimeters. The density of the liquid is 800 kilograms per meter cubed. Calculate the difference between the pressure of the gas and the atmospheric pressure. So we use pressure difference is equal to rho gh or delta H. Rho is 800, g is 9.8, and h is 2 divided by 100, which is 0.02. This gives an answer of 156.8. We can approximate that to 157, and the unit here is Pascal. Triple I says a similar device with a tube of smaller cross-section area is connected to a gas supply at the same pressure. State and explain the effect on the value of H. We say that H depends on density of liquid and pressure difference, which did not change, so H does not change as well. Question 5 is about thermometers, which were also removed from the syllabus, so you can skip this whole question. Part AI says in the space below, draw a label diagram of a structure of a thermocouple. Thermometer include the device from which a reading is taken, which is a voltmeter. We draw it as a circle with a V inside. We have two wires coming out of the voltmeter and the third wire connecting the two ends of the wires. One of them is called the hot junction, the other is called the cold junction, which is immersed in pure melting ice. We can draw something like this and just label it pure melting ice. Now the two wires coming from the voltmeter are made from the same metal. We can call it metal 1, or we choose one type of metal, and the wire connecting between the two other ends or the two junctions must be of a different metal, so we can call it metal 2, or we choose another type of metal. For example, the two wires from the voltmeter copper and the other wire is made of tungsten, for example. Double I says a thermocouple thermometer is used to measure the temperature of the flame of a small candle. State 2 reasons why the thermocouple thermometer is suitable for this application. It can read high temperatures, like the temperature of the flame, and it can measure small surfaces or measure on small surfaces. Part B says state and explain any effect on the sensitivity of a liquid in glass thermometer of reducing the diameter of the capillary tube. This causes the increase in length per degree or per degree Celsius to be greater, so sensitivity increases. or we have higher sensitivity. For double I, increasing the volume of the liquid-filled bulb, so more liquid means more expansion, again per degree, so again higher sensitivity. Question 6a says state 3 factors that determine the rate of evaporation of water. You can say temperature, wind speed, surface area, or the amount of humidity in the atmosphere. Part B says a person climbs out of a swimming pool and stands in the open air. Explain why evaporation of water from the surface of the person's body causes the person to feel cold. We say that the most energetic molecules absorb energy from the body to overcome intermolecular forces and escape, leaving the rest of the molecules at a lower average kinetic energy, which represents temperature. Since the kinetic energy decreases, the temperature decreases. Question 7a says a laser produces a beam of monochromatic light. State what is meant by the term monochromatic light. It is light wave or light made of one frequency or one wavelength. Question B says a wave in air is incident on a glass block. Figure 7.1 shows the wavefronts at the air glass boundary. The arrow shows the direction of travel of the wavefronts. The wave undergoes reflection and refraction at the air glass boundary. On figure 7.1, draw first the wavefronts of the reflected wave and then the wavefronts of the refracted wave. So we can sketch or use a protractor to measure the exact angle between the wavefront and the boundary and draw the same angle from the other side. So something like this. And then at the intersections between the wavefronts and the boundary, we draw the other wavefronts parallel to this one. So this is the second one, third one, fourth one, all parallel to each other. Fifth, two more, and the last one. Now the size of the reflected wavefront keeps decreasing because the amount of the reflection of the wave keeps increasing going into the glass. For example, this has a small part that was reflected, this has a larger part that was reflected, and so on. As for the refraction, going from air to glass means that the speed decreases and the wavelength also decreases, so the distance between the wavefronts decreases. Now, if we try to bend the wavefronts this way, you will find that the wavelength will increase, so we bend them the other way, so like this, and we draw the rest of the wavefronts. We will find that, yes, the distance between the wavefronts will actually decrease, showing that the speed decreases. Fourth one, fifth one, two more, and the last one. Again, we have different size of wavefronts here. So this is the reflected and this is the refracted wave. Part C says a transverse wave is produced in a long horizontal rope. The rope is much longer than the wavelength of the wave. In the space below, sketch a diagram to show the appearance of the rope as the wave passes along. Label two important features of the wave. So as a guideline, I'm going to draw a horizontal line. This is not part of the wave. This is just a guideline for me to draw. And we have the shape of a sine curve like this, continuing further. And the two important features are the wavelength here. So we label this wavelength. It could be between any two identical points. I chose that it is between two crests. It could be between two troughs or 2 points like this one and this one. They are identical. And the second feature is the amplitude of the wave, which is the distance from the central line to a crest or to a trough. So this is the amplitude. We label it like this. And this is our diagram. Question 8 says a vibrating source on a ship produces a sound wave that travels through the ocean. The wave produced is a longitudinal wave. Explain what is meant by the term longitudinal wave. We say that the displacement or the vibration or the oscillation is parallel to the direction of energy transfer or direction of propagation of the wave. This is the definition of a longitudinal wave. Part B says the frequency of sound wave is 800 Hz. The speed of the sound in air is 330 meters per second. State a typical value for the speed of sound in a liquid. So for example, in water, it is 1500 meters per second. You should memorize this. Double I says using your value from BI, calculate the wavelength of the sound wave in the ocean, which contains water. Wavelength is equal to speed divided by frequency. We have the speed 1500 and we divide by 800 to get the wavelength. That gives an answer of 1.875. We can approximate that to 1.9 meters. Question 9 says figure 9.1 shows the symbol for a 12-volt battery. Part A says two lamps are connected in parallel with the battery. On figure 9.1, using the correct symbols, complete the circuit diagram drawing the two parallel lamps. So a lamp is a circle with a large X inside of it. We have two of them, and we draw the terminals of the lamps like this, and we connect them as branches to the battery. So this is the other branch here. This is the meeting point and meeting point of the branching of the parallel connection. Part B says one of these lamps has a resistance of 6 ohms. Calculate for this lamp the current. We have the voltage 12 volts and current is equal to voltage divided by resistance. So 12 divided by 6, that gives an answer of 2.0 amperes. And then we are required to calculate the power. Power is equal to VI or V squared over R. If you do not want to use the current, which could be calculated wrong. Using V squared over R, we have 12 squared divided by 6. That gives an answer of 24 watts. Part C says the power of the other lamp is 36 watts. Calculate the total energy delivered to this lamp in 20 hours. Energy is equal to power multiplied by time. So 36 multiplied by 20, but this is in hours, not in seconds. So we multiply by 60 minutes and then by 60 seconds to get the answer in SI units. The answer here is 2,592,000. We can approximate that to 2.6 times 10 to the power of 6 joules. Question 10 says a transformer consists of two coils of wire wound on a metal core. Figure 10.1 represents the transformer. State the name of the metal from which the core is made. It is iron or soft iron. B says the primary coil of the transformer is connected to the output voltage of an AC generator, which supplies an alternating current. Explain why there is a voltage between the two terminals of the secondary coil. This is basically a question about how a transformer works. We say that the AC in the primary coil creates a changing magnetic field, and the iron core strengthens the magnetic field, so it reaches the secondary coil, and then the change in flux or the cutting of the magnetic field in the secondary coil induces an EMF or voltage in the coil. Double I says there are 560 turns on the primary coil and 910 turns on the secondary coil of the transformer. The voltage between the two terminals of the secondary coil is 78 volts. Calculate the voltage supplied by the AC generator, which is the primary voltage for the transformer. We can use Vp over Vs is equal to Np over Ns. Vp is unknown, Vs is 78 volts, Np is 560, and Ns is 910. Then we cross multiply 78 times 560 divided by 910. That gives an answer of 48 volts on the primary coil. Part C says transformers are used to increase the voltage when electrical energy is transmitted in cables across long distances. Explain why power losses in the cables are lower when the voltage is high. We say that when voltage is stepped up, the current decreases, which decreases the heating effect of the current in the cables or the transmission lines. Question 11a says figure 11.1 shows data about 9 elements. Carbon 14 is a radioactive isotope with a nucleon number 14. It decays by emitting beta particles. Use any data you need from figure 11.1 to write down the nuclide equation for this decay. Now for carbon we have the proton number 6 and we have the nucleon number 14. We can use the equation for the decay. So carbon 14 nucleon and 6 proton numbers, and we have a beta emitted which has numbers 0 and -1. So the new element must have a nucleon number 14 because 14 plus 0 is equal to 14, and a proton number 7 because 7 minus 1 is equal to 6. So we check the table for a proton number 7. This is for nitrogen and the symbol for nitrogen is N. So we complete the equation by writing here N. Part B says a radioactive sample is placed close to a detector. The radioactive isotope in the sample has a long half-life. The detector records a count rate of 597 counts per second. Figure 11.2 shows the readings when different materials are placed between the radioactive sample and the detector. We have a sheet of paper, we have a piece of thin aluminum, a piece of thin lead, and we are required to explain whether any of the alpha or beta or gamma radiation are emitted from the radioactive sample. So first, the reading was 602 with the paper between the source and the detector, and the initial reading was 597. These are very close to each other, so there is no significant decrease when adding a sheet of paper, so alpha particles are not present or not emitted. Adding a piece of aluminum should decrease the amount of radiation if beta particles were present, but 598 is very close to 597, so no significant decrease. So beta particles are not emitted or not present. When adding lead, the reading decreased from 597 to 510, so that was some effect, which means some of the gamma radiation left was absorbed by the lead, so gamma rays were emitted or were present in the type of radiation going to the detector. So this was the end of the exam. I hope you enjoyed this video and found it useful. Keep practicing, and I will see you in another video.